Hey, hello there, and welcome back. So, Advent of Code, day 18. Have the code as I left it yesterday, and well, also yesterday after recording the solution for part 1, I read this Wikipedia article for the Shoelace formula for determining the area of a polygon. And I was very tempted to implement this yesterday, but it was already like 2 a.m. and I was pretty tired. So, okay, I thought let's give it a shot today better. So, what is it that we did? Yeah, the puzzle for this day basically asks you to follow these instructions, like going right 6, going down 5, and so on, and you make a shape like this one, and then calculate the area of this shape. So basically it will be this thing. And for part 1, what we did was a simple fluid filling algorithm to like start filling a point inside of this and just fill everything. But on part 2, you basically are asked to do exactly the same thing, but instead of interpreting these numbers, you are interpreted these numbers, like you decode these hex values. Like it was actually a total misdirection to talk about hex colors, and instead of colors, they are like the actual instructions. You basically extract 5 hex numbers, and that is the amount of the amount of units that you have to go in that direction, and the last number is the direction itself. So they are much bigger numbers, as you can see that they are like almost 1 million, and the number that you get was like in the billions basically, or almost 1 trillion for this simple example. And of course the actual input is much longer, so doing the fluid filling won't work. And well, I had a suggestion, or maybe I should say spoiler, by a friend that commented that he implemented this Shoelace formula for this puzzle, and it seems to be simple enough. That there is different ways of doing this, but they are all pretty similar. They are basically a sum of some products of things. I liked this one especially, which is the Shoelace, that you are doing like this matrix determinants, and I didn't remember what this was, but it's a very simple calculation. Basically here there is a concrete example. Matrix determinant is basically this times this minus this times this, and so on. So here it would be 3 times 2, 6, minus 7 times 1 is minus 7, and so on. And you repeat the starting point 1, 6, right? That is x1 and y1. Yeah, you repeat it at the end also, and that maps very well with what we are doing here, because we are basically drawing a polygon and then finishing where we started. I don't know if it's exactly where we started or one before, so let's check the example. Here we are starting here on the top left, and we go 6 to the right, and then at the end we do a up 2 after a left 2. So yeah, left 2 left us here, and then doing up 2 leave us again at 0, 0. So yeah, we can probably assume that is the case for the sample and for the actual input, and try to implement the Shoelace formula for this. So we have the code for part 1. Actually, let's close everything else. I want to maybe have an even simpler example for this. Now this is day 17, sorry. The sample here is this. Let's copy this and call it sample square, like a very simple square thing, where you go to the right, let's say 2, then down 2, then left 2 again, and then up 2, and then get rid of everything else. And the hex values are not important, so we can just say, I don't know, 0, 0, 0, 0, 0, 0. Like, those are non-important. Yeah, whatever. Like, I want to, because basically if we do the shoelace formula implementation, that can work for part 1 and part 2. Like, we don't need to do like fruit filling for part 1 and the shoelace formula for part 2. So what we were doing here on part 1, we're parsing the instructions, then we sort of iterate and collect the we iterate the instructions or the dig plan, and we save all the positions that we go through in this trench hash set. I think we're not going to do that. Yeah, we're not going to do any of that, or we are going to do something pretty different. Like, we don't need to count up every step. We can just, I want to collect all the points in this polygon. So it will be this point, this vertex, this vertex, this vertex, and so on. So this can be done in a much simpler way. So yeah, let's actually have this. Like, I want to get rid of most of these things. This is basically the parse instruction for part 1, let's call it. And then we probably will have something different, like reinterpret the same instructions but for part 2. Yeah, this is the dig plan for part 1. You know what? Let's get rid of basically everything. Yeah, this I don't need. The printing of the trench is also something that's probably, like, if I'm not going to collect every point, there's also no point in having that. And the dig interior is the fluid filling thing. And look at that, we had to de-hard code the starting interior point because I just hard coded it to get an answer. But we won't need to do that because this approach, we are not going to follow it. Okay, so we have another dig plan. What are we going to do? Well, let's first draw the polygon, or like collect the points in the polygon, which should be pretty simple. Is this a fold? Can this be implemented? It's almost like a fold, but collecting, like, we could do it with a for loop, of course. Like, let's say, let's mute. Well, this is something that was already here. Actually, there was a little bit of logic that I removed that maybe I didn't want to remove. Yeah, here when you're walking. So let's remove the dig interior thing, the printing thing, and up to here. And the trench. Well, let's remove the min-max things and this. But the movement is kind of similar, not quite. We're not going to do a for loop either. Yeah, let's leave this like skeleton loop. Instead of having a trench now, we're going to have a polygon, let's call it. And is it a hash map? No, it should be a vector of things. So let's actually start and make it a vector of well, xy to start, because yeah, we need this initial point. And then we're just going to increase xy not by 1, but by the count that, like by these numbers directly, right? And by the way, I wanted a very simple sample because this would be drawing, like if you start, this would be drawing basically this, like go right 2, then go down 2, then go left 2, well, if I can write, and then go up 2, it would be drawing this square, which should be area 9, of course, 3 by 3. So one interesting thing, okay, let's just simply do this, and this, and this, and this, and then push this into the polygon. I think that's a way to get the polygon itself. We can probably print it. Print len. Sometimes forget to do this polygon. And let's actually run this with the sample, like the square sample. Yeah, 0, 0, 2, 0, 2, 2. Okay, and it ends up at 0, 0. Great. Actually, let's also run it with sample inputs from the puzzle description, just to check that it ends in 0, 0. That's correct. And if we run with the actual inputs, oops, what happens? Oh, subtract with overflow. Yes, because these things are not, they shouldn't be U32. Let's just have these things be 64 signed bits, 64-bit signed integers. So we can go, like the directions, the x, y can be negative. So we do this, and the last number was, again, 0, 0. Okay, so all the polygons that we have end up at 0, 0. That's nice. So the first point in the polygons gets repeated. We can apply the shoelace formula directly. There's probably a much better way of doing this this thing instead of using a for loop, which I don't know, because using a fold is kind of similar. I know that there is let me see, dig plan. There is a scan method on iterators, which is like super powerful. Like fold holds internal state, but unlike for, produces a new iterator. Yeah, this is sort of what we want, right? You start with initial state. These two arguments, system internal state and enclosure. It is kind of assigned into. Yeah, it's a bit of a weird thing, but it's. Let's rewrite this with scan and see if it's better or not. So you start with an initial state, which would be 0, 0 basically. This could help us like not have mutable state. So that is the calculation using mutable state. Let's see if scanning could be better. The state that we'll have is basically the x, y coordinates where we are, and then we'll have the instruction of the dig plan, which is going to be, well, we can call it instruction maybe. or just destructure it here, why not? The dir and count, right? So we're basically going to do the same thing. XY is going to be mutable references now, so we can dereference and assign. And this is complaining probably because this is a reference. Yeah, let's dereference here, no problem. And now your problem is that I'm just returning this match. I should be returning, it expects an option because you can probably early terminate this thing, but let's just return XY basically. Right, and or dereference these two things. And your problem here is no, sum, not the results, an option. And yeah, we're moving there. Yeah, we can make this thing be copy and clone and blah. Okay, and then the dig plan, we consumed it here. Sure, and now we are not using this. What we will then do is collect these values, I guess, into, let's say, let's polygon 2. We need to say the type, but okay, the type is correct. And this thing is basically the same as this thing. Is this better? Questionable, but I actually don't know if it's better. Let's if it's the same, because I think I will be missing the starting point. Let's run it with sample square. Yeah, okay, in polygon 2 we are missing the starting point, because yeah, that is like the seed for this, but for this scan, but we would need to yeah, we would need to also have it as like the initial thing. So we could fix this. I mean, we could have something like saying, okay, let's start with a vector that has these points and then extend it. This extends returns something. It just takes a mutable self, but it's not too great. What does concat do? I always oh, concat is, it's a weird thing. I didn't know that concat did that. It's not what I wanted, but it's interesting. It's definitely interesting. But yeah, we basically would like to put all of this into like an iterator starting with that. I mean, yeah. I'm going to keep the for loop for now. If I can think of something better, I'll do so, but this seems a bit more simpler to me. Man, I have trouble like letting go of things. Let's actually try to do it like completely, like get the two polygons as the same and see how they actually look. So we'll start with 0, 0, and then we'll do, I need this thing to be mutable, unfortunately, but then we'll just do what's extend with an iterator, and we don't need to collect, I guess, here. Would this work? Are these two things now the same? Yes, they are. I mean, it looks pretty similar to this. I mean, here we have this mutable thing, but it's basically the same thing that we have here. In fact, like, this thing is the initial thing, and we're getting past mutable variables here. So it's basically the same thing. I think I do prefer the for loop. Yeah. So okay, that was just how do you say, like a sidetrack. So okay, we do have the polygon. Now, if we do the shoelace formula for this polygon, the answer that it will give is actually wrong for this square. Because we said that this square is drawing a 3 by 3, like this 3 by 3 square, but as you can see, like, the coordinates that get printed like goes from 0 to 2, so this is a 2 by 2 square, and the shoelace formula will give the answer 4 if we implement it correctly. Like, the area of this square is 4, and the difference lies in that these are basically things with thickness. Like, they represent a 1 meter by 1 meter cube of thing that is getting digged, and that thickness is what makes things a bit more complicated, because this is basically like the coordinates, these 0, 0 coordinates. You can imagine it as the coordinate of the top left point in this little square, and then this one, which would be 2, 0, is this coordinate, and this one is 2, 2, is this, like, the top left corner of the little thing. So if we actually wanted to use the shoelace formula directly, the polygon should start, like, we should consider this thing 0, 0, but these should give us the corner 3, 0, and this should be 3, 3. And in order to do that, you would need to know, like, which direction you're turning. So here we would be going right and then turning down. So if you can imagine, like, by the way, this is a polygon that is like going clockwise, and the actual sample is also a polygon that goes clockwise, and my actual input is also a polygon that goes clockwise. And the fact that it's going clockwise, it means that you can imagine it here, like, if you were following this path here, the interior is always, like, to your right, if you're going clockwise, and if you're going anti-clockwise, the interior of the polygon is to your left, basically. So if we know that we are going right and then down, we know that this vertex is like the exterior of this one thickness path, or this path of 1 in thickness. So we could put that logic into, like, it would make the logic a bit more complicated, because we would need sort of a slicing window, overlapping window of, like, what is the current direction and the next one, to know, like, what corner it makes. But we could make that work, but I'm wondering if it's even necessary, if we cannot do something different. So okay, let's first try to implement the shoelace thing. So let's get say let's area, or like polygon area, can I call a function that is called the same? Because I want to call the thing the same thing as a local variable. Polygon area for this polygon. And I think there's no problem in doing so, like having a local variable being called the same thing. I'm not sure, but let's see if that's not a problem. So the area, we're passing I64 here. Does it make sense to have? Yeah, let's use signed numbers for everything. Like, it doesn't make sense that the area is signed, but don't care. Here we need to do finally the shoelace formula, and once again I forget a bit late in the video to put a stopwatch, so I don't know how long we have been going, probably like 20 or 30 minutes already. So on this shoelace formula, we are basically going to need to use sliding windows of 2. So, and this already ends in the same. Yeah, I think if I want to, it's a very nice, pretty formula. And actually, like, I've read this article, or like most of it, I think. The formulas, when you get like the geometrical interpretation of what they are doing, they are not like that magical. Like they look magical at first, but this, especially the trapezoid formula, like what you're calculating, actually makes a lot of sense. It's not the kind of thing that you couldn't come up with, although it is like quite awesome that people in the 1700s came up with this thing. But I mean, with modern math and calculus and this kind of thing, is like this sort of thing is not so difficult to like reason about, but still it's a very nice theorem or formula. So okay, we are going to basically take each pair of points in this polygon. I think we can do this with, let's try to do it just with iterators in this case. Let's say Windows is kind of what I want, but I think I prefer the there are circular tuple windows in iter2. That's really neat. This could actually have been used the first one. This could actually have been used if I didn't have like the first element repeated, or I just want to like loop around. So if we were generating the polygon like with that scan method that was not included in the first, so that's interesting. But normal tuple windows would be good for me. So I want to basically map these tuples, and we're going to take tuples of 2 elements. So they are going to be 2 points in the polygon. We could call it point 1 and point 2, I guess. And then we're gonna sum all of this, right? And instead of saying point 1 and point 2, let's just restructure this. It's gonna be x1, y1, and then x2 and y2. Okay. And then what we do is, let's remember, xy times y2 minus y2 times x2 times y1, I think. Isn't there a, yeah, here, like x1 times y2 minus x2 times y1. Yeah, That's exactly what we want. So it is x1 times y2 minus x2 times y1. So like kind of a sort of weird cross product. And your problem here is like, oh, I almost screwed up. Like yesterday I have a similar screw up of like repeating. Was it yesterday or before? Like I repeated like a variable name and got like between x and y, and I just used y twice, I think, and I just screwed everything. So okay, this was simple enough. If this is correct, let's see what the polygon area is for our square, which I predict should be 4. No, try from slice iterator error. Try from slice iterator, and unfortunately the errors when you do this sort of propagation, they don't print stack traces. I'm pretty sure of that. So if you do rust stack trace 1 of this, no, and try from slice. Oh, was it because I left? I think it is because I left this drawing here, and on the parsing we are trying to convert a slice into an array, I guess, or into another slice of a fixed width. So probably that was failing. 8. Oh, 8 because I think this thing gives us 2 times the area. Yeah, 2 times the area. So you have to divide it by 2 basically. So this is sum, divide by 2. What a beautiful. Come on, sum. Twice area. And you can be again an x64, be happy with that. So now it should be 4. That's great. That's not exactly the answer that we want for our little fella, this guy, but I'm thinking that we can probably add the rest, because basically this is a 2 by 2 square that we are calculating in the Shoelace formula. You can think of like if you move that square like to the middle here, so it's like centered, and if like it's offset by half a little square, half a tile, it's like the area that we need to add to be the right answer corresponds to the length of the like the perimeter of this polygon. Perimeter is the perimeter should be trivial to compute because we have all the lengths, and the perimeter of a 2 by 2 square is well, 2 times 4, it's 8. Divided by 2 is 4, and I think we just need to do like the perimeter divided by 2 plus 1, because basically each corner when we are turning when it's a clockwise polygon, each of the 4 corners that are like extra adds a quarter of a tile. That's kind of my intuition. I'm not sure if that will I'm pretty sure that will work for a square, but I'm not sure if it will generalize to like the sample and the actual input. So let's try it out. This is the polygon area. Computing the polygon perimeter. I'm not sure if that's the word that's usually used for in English for like the perimeter. But this should be easy to compute. We're just going to iterate over the polygon. No, over the polygon, no, over the instructions actually. The dig plan is going to give me that. We're going to iterate, we're going to map, and the dig plan has a direction which we won't use, sorry, and a count which we will use, and we just map into the count. And then we sum these things. And this should be an I64, I think. And then I would say that the total area of like the lagoon that we are digging, let's call it lagoon area, is going to be the polygon area plus the polygon perimeter divided by 2 plus 1. So let's print this. This I'm pretty sure it should work for the 3x3 square, and should generalize like if we make it one longer in each direction. This should now be a 4x4 square, and its area should be 16. And basically the polygon area would be 9 now, and the perimeter of the polygon would be, well, this polygon that we are having is a 3x3, so the perimeter is 3 times 4 is 12, divided by 2 is 6, plus 1 is 7, so 9 plus 7 is 16, which is a 4x4. So this I think generalizes correctly for that little square, but does it work for the actual sample? I have no idea. 62. Was this the correct answer for part 1? Yes, respectable 62. Awesome. And what about the actual input? Sure. Did I run it correctly? 70,253. Yes. Okay, this did generalize quite well. I was worried that maybe I would have to implement this logic of like taking into account the little turns, like going right and down, doing like, okay, it's the x plus 1 and same y, and it wouldn't have been such a difficult logic to implement, but I'm glad that it wasn't necessary, it seems. So okay, now we can implement part 2, I think, pretty easily. We just need like a different parsing, and we should be good to go. We can even like have a parse that parses the 2 instructions for part 1 and part 2, and then like separate them. Was there a thing that I think when you collect you can do that? Rust collect or Rust unzip, basically tuples into 2 vex, something like that. Yeah, collect vex of tuples into 2 vex. That is exactly what I want. Iterator unzip to the rescue. Oof, there is an unzip. That's really nice. That's really nice. So, and let's try that out. Does it make sense? Because here I'm already like splitting this into the 3 components, so since we are already splitting, we can probably do it. So okay, let's actually add these things because it's a better part 1 solution. The sample square is I don't know if I will use it as a sample. Maybe it would be a good example to add to like justify this thing. It's like, hey, you know, if you have trouble understanding this, like check out the square sample, maybe. But yeah, this is basically, let's actually extract all of this into a function. Call this thing compute calculate, let's just say lagoon area, or like get lagoon area. I never know how to, like, what verb to put, like calculate, get. Get is fine. Yeah, get is fine. Sure. And we don't need to pass. Let's pass this thing as a reference, and here just take a slice of these guys. Right? Yeah. We make the polygon for this plan. And then we just return this. We can inline this variable, of course. Get lagoon area. The polygon area. It's also call this thing get polygon area, just for consistency. Okay, and we're gonna have basically this thing try collect. What is the unzip? The unzip thing. So from A and from B. I'm not sure about how will I deal with errors here. Like if it's easy to propagate them up. Maybe it will be possible, but I'm not sure. Let's actually try it out kind of quickly. This is going to be part 1 instruction. I mean, does it make sense to do this? I think it doesn't, right? Why would I do that? Do we have something like, let me see, split once, but split once like from the right, first stir, split once from right. Yeah, I think I'm overcomplicating things by trying to unzip this. Let's just do, as I have here, like parse instruction for part 1. So this is the, we try collect, sure. This is the dig plan for part 1. Lagoon area, let's be consistent also and just call it P1, lagoon area, part 1, and then we're just going to repeat these these things and say dig plan part 2, it's a different parsing, and we can even put these things in here, like sort of inline this, get lagoon and get for part 2. That's not the. Let's actually do this. I wanted to inline it, but I really dislike the formatting of like when it tries to print, but it spans multiple lines. So okay, now we can parse. We can have a little bit of repetition, but it's better than having everything crammed into the first thing. So here we're basically going to do the same, I think. Yeah, we can do this, but we can like ignore the other two and just keep the hex color. Actually, let's call it hex, and let's check the sample. So in the sample, we are having, let's see, what did we have to do? Basically, we need to just get the number from here. Yeah, get the hex characters. Probably do that by, well, we could strip, because also we need to get the first 5 to do something and the last one to do something else. So how do we do that? I think we can ask for a given character. We can ask it like, is hex, yes, is ASCII hex digits. So uppercase A and then A. This is ASCII, and A is also ASCII hex digit. That's nice to know. We can probably extract this. Sure, right. We do that, and then we try to parse, or I guess we can also like strip this, strip that, assume that everything inside is hex. That sounds a bit simpler. So let's do this thing returns result, right? Yeah, because it can fail unexpected direction. Let's strip it and say hex. Prefix. What is your type? Aren't you a string? Why is it unknown? Collect vec. Yeah, I mean, shouldn't you? In fact, like, is it necessary that you do? Sorry, I'm getting a bit confused here. Is it necessary that you, like, why is it unknown? And here it's, it also says unknown. That's weird, right? Maybe Rust Analyzer is having a problem with this. I wonder if it's actually necessary to collect this into a vector. Yeah, I guess it is. Okay, weird, I think. Kind of weird. I think I need a strip prefix here. Yeah, it takes one argument. The prefix that I want to strip is this and this. and this will give me an option. So that's kind of ugly, but let's just say, and then yeah, strip prefix of this. I'm gonna say okay, or invalid hex. Beautiful. So now hex is still a no, but should still be a string slice. We're gonna also like split into two, I guess. The first 5 digits is the number part, and the last one is the direction. So let's say let hex number is gonna be hex from 0 up to 5. We can, yeah, and parse and propagate anything. Oh, this is actually parsing a number on base 16. How do we do that? Do we have like I64 from stir? Is what I want from stir radix converts string slice into. Yeah. This is what I want. This is what I want. And it's base 16, also known as hex. I guess this will give me a result, right? Yeah. And this, we need to take a slice, sure. And why are you failing? Cannot index. Oh, this is a. Oh. Look at that. It says that this is like never type. That doesn't make any sense. Hex number. Okay, now that should be fine. And the direction, we are not going to. Well, it's actually not the hex number now. Like this is the actual like count. We don't need to parse here. The direction is going to be like hex. The last is a string slice, so I guess we can say last. Let last digit be this. Okay, or invalid hex. Last digit. Stir is not an interpreter. Doesn't string has have a last char or something? Okay. Yeah, I guess we can do that, but do I want to? Don't think I want to. Let's make it like this, maybe. You can probably check the length of the hex to be 6, since we are assuming that here. I'm gonna leave it as a comment. Ensure hex length is 6. Yes. Okay, so we're going to map the last digit, and this can be basically, well, a digit. 0, 1, 2, 3, and this I think went in. 0 means right, 1 means down, 2 means left. Okay, so it starts from the right and goes in clockwise direction, so it's gonna be right, down, left, up. So almost the other way around of what we did. Sure, unexpected direction, last digits. This probably wants us to be a little character. Okay, so is this correct? For example, I have no idea. Let's just try it out for the sample, which we have the invalid hex. Whew. Awesome, and I think it's this. Oh, because I'm stripping prefix twice. It's gonna be suffix here. Okay, let's go now. That is a much more respectable number. Is this the correct answer? Is it? Yes, it is this number exactly. Thanks a lot, Shoelace formula. Sample out for day 18. We want this. And of course, let's just run with the actual input. And it's this giant number, which is in the order of, I don't know, that is a million, that is a billion. No, sorry, this 131 trillion, I think. That's a big lagoon. And these are cubic meters of lava. Is this the correct answer? Yes, it is. Okay, awesome. Thanks, maths. That was pretty nice. The parsing was actually much more involved than the actual calculation. So that's interesting. Okay. And we have part 1 and part 2 already like quite neatly separated. So these are the actual answers for this day. Let's copy this into the answers file. This would be day 18, would be this. And if we run now, check all. Sure, everything passed. The sample square is not being checked because there is no out file corresponding to it. You can see already here, Lavaduct Lagoon is being checked with a sample, but let's actually maybe put a sample square. No, not this. This out should be, what should it be? So it's a square of 3 by 3, so this should be 9 for part 1. And the part 2, I guess we can put the hex numbers, like we can also make a big square, or bigger square, I guess. These are hex numbers. So yeah, we can maybe make it the same. Why not? This should also be 9 by 1. Yeah, 3 by 3 basically. So we can use this as a very simple example. Let's go to the code. This is now code review time. So okay, the main function looks totally fine. Nothing weird there. We can even get rid of this and make it a bit compact. This get lagoon area, I think I pretty much like what this is. we can even here, this is the building of the polygon. That's fine. Yeah, it's fine. Get polygon area. We could extract this into like get polygon perimeter, but it's just simple. Yeah. We could even like not even build the polygon itself, because this could just receive an iterator of points. But I mean, there's no need for that. There's no need for that. This to do, we can totally do this. So okay, let's finish reviewing this. I'm okay with this. I could extract this into like a build polygon for a given dig plan. Let's see how that would look, but I'm not I don't care that much about it. So this could be called build polygon for a given dig plan. We're gonna, I should have said this. Polygon area. Yeah, I mean, it's fine. Yeah, let's leave this instruction. This compute the polygon area doesn't take into account the thickness of the trench. Which adds this extra area based on the polygon perimeter. Okay, check simple simple square sample in sample square txt. File as a simple example of this. File, let's say, for a simple example of this is fine. Not just simple, for an easy to understand, let's say, file for an easy to understand example of this. Okay, this should build a polygon. Nothing too fancy about this at all. The polygon area, so we can add some actual documentation for this. Calculates the area of a polygon using the Shoelace formula. And we can even have a link for the Shoelace formula. Look at us being nice citizens and and having see this. Okay, look at that. Awesome. And then we have the two parsing functions, which is, I think it's fine to have like two different functions for this, because like the first parsing was quite simpler. The second one is a bit more involved. We are sort of expecting these things. I would like to say, like for hex, just you know, make a slice of everything that is hex numbers, and that's it. I think that shouldn't be too. Yeah, let's add everything that we have now so far. So up to here, I would say everything looks pretty damn right. Can we do something here simpler, like what do I want? Like the thing is that, yeah, if I do like a split by things that are not hex numbers or something like that, I would also need to collect this. It's not particularly nice either. Yeah, but what if we do like, you know, get the characters, filter the ones that are actually the like char hex is ASCII hex digit, like filter these guys and like just collect into like string. Like, does this work? It seems, well, at least it compiles, and then we just extract this and this, and yeah, this is, I think, better than being like stripping the prefixes and things like that. If we run this, yeah, it passes. And what didn't pass before? Oh, I think it was just a square sample that we needed to add the output file. Okay, so yeah, this is, even though it does an extra allocation for this, which is unnecessary, I don't really care about that. I do prefer like the simpler to understand code, because this is not a hot path or anything. So yeah, then we get the +5. Oh, we would need to do checking of this, and we cannot, like, if we do assert, like assert EQ here, the hex length to be 6, like this would work, but it would panic if it failed. I would like to have something like this, but that returns a result instead of like panicking. And I looked for this already, and it seems like, well, it doesn't exist on Rust standard library. Of course, we can also like implement it manually and say, hey, if this is not equal to 6, then, and of course these parentheses are not needed, then return an error and say like expected 6-digit hex number, something like that, and early return from here. Like, yeah, this works actually, and is what I want here instead of the assert. But I also learned that there is this anyhow library that has an ensure, I think it is, macro that does exactly, like, it was like an assert, but it does exactly that. Like, it propagates, like it gives you back an error and propagates it up. So I think I would be interested in maybe trying anyhow, and instead of using like my own AOC results, just use anyhow result, which is basically a very similar thing but more powerful. It's It allows to pass those results between threads, basic things that you would need to expect to work, but doesn't for results of dynamic errors like we have here. And it also, most importantly, it provides stack traces. Anyhow provides stack traces, while the Rust standard library results don't. So I think that's the biggest, what makes anyhow most attractive for me. But for now, maybe let's leave this assertion as this. We can refactor it later. Yeah, and the rest of this thing is pretty trivial, so that's fine. That is fine. Sure. Count and last digit. Since this is the direction and we return first the direction, then the count, let's move it like this. We have the direction and count. Although the count is first, so I'm a bit hesitant with this. Yeah, this is nice. This was pretty good, and I had no idea about this shoelace formula. Let's actually make a little thumbnail for this. We had this printing of the map. Now it would be impossible for such a large lagoon, but we can still do our usual. I don't know what's my usual font size here. If we clear the screen, we can put this over here. And if we clear the screen and do a toilet of day 18, and what did we do today? Well, shoelace formula could be polygon area with new line shoelace formula. How does this look? Yeah. This looks, well, this is very descriptive of what we did, basically. And the code maybe could showcase a little bit of that, even though this is for a thumbnail and it's impossible to read code on a thumbnail. So, yeah, I'm glad. Well, today I learned something new. There exists a simple formula to calculate polygon areas. That is something that I didn't know before, and I think it could have helped in some maybe previous Advent of Code puzzles. The pipe maze one from this year could probably have been solved with that, but yeah, for this one it was, I think, almost a necessity. I don't know if I could have thought about another way to solve this. So, well, I think that will be it for this video. If you have been watching thus far, thank you very much for doing so, and see you later. Bye bye.